The peculiar aspect of exotic matter, aside from its composition of strange quarks, is its highly contagious nature, akin to a superinfection disease. Moreover, exotic matter is so stable that every substance in the universe desires to transform into the exotic matter for the sake of stability. It is delightful to greet you all once again in Enigma's Cosmic Video. One of the reasons why many people perceive astrophysics as incredibly complex is that no one tells you how remarkably simple it actually is. For example, let's consider stars, one of the most widely discussed entities in the field of astronomy. The life of a typical star is sustained by the energy released from nuclear fusion reactions occurring in its core. This energy radiates outward, balancing against the inward gravitational pressure. When a star exhausts its fuel, its core collapses to an unimaginable degree, resulting in the formation of entirely new types of objects. The ultimate fate of these objects depends on the initial mass of each star. Sun-sized stars, for instance, collapse into white dwarfs, celestial bodies roughly the size of planets primarily composed of oxygen and carbon atoms densely compressed. Larger stars, on the other hand, explode in cataclysmic events known as supernova, leaving behind remnants such as neutron stars. Neutron stars are incredibly dense objects, far denser than white dwarfs. A neutron star can have a mass ranging from 1.1 to 2.1 times that of the Sun, with an average of about 1.4 solar masses, packed into a diameter of only 20 kilometers 12 miles, comparable to the size of a coffee spoon. Depending on its location, a neutron star can have a mass equivalent to 5 to 600 million tons, roughly the mass of an adult African elephant or 92 Great Pyramids of Giza stacked together. As the name suggests, neutron stars are predominantly composed of pure neutrons, making each neutron star essentially a gigantic atomic nucleus spanning tens of kilometers. Similarly, the heaviest stars in the universe give rise to the densest evolved objects known as black holes. However, life is not just about light and darkness. If you pay close attention, you will always find hazy, intertwined regions between the two extremes. Scientists have long proposed hypotheses regarding what lies on the boundary between the existence of a neutron star and a black hole. In this video, Enigma will dare to venture into exploring that boundary. Welcome to the cosmos, where 121 peculiar stars reside. The strangeness of neutron stars is profound to the extent that physicists still do not fully comprehend them. We can observe how neutron stars interact with surrounding objects and make accurate predictions about the behavior of neutron matter near their surface. However, understanding the core composition of neutron stars remains elusive. Neutrons are subatomic particles, but they are not fundamental particles. Fundamental particles are the smallest constituents of any matter. Neutrons, on the other hand, are composite particles. They are made up of smaller particles known as quarks. As we know, each neutron and proton is composed of 2 down quarks and 1 up quark. The question arises, if we compress a large number of neutrons together, will they form a gigantic quark ball? Or would compressing even a single neutron result in a massive quark ball? The answer is that physicists are uncertain, but it is possible, albeit complex. Under extreme temperatures and pressures inside neutron stars, neutrons are typically kept apart by a degeneracy pressure, which is essentially a pressure exerted by the neutron particles under tightly squeezed conditions. It is this degeneracy pressure that allows neutron stars to exist in a stable state and counterbalance gravitational collapse. If you were to compress a neutron star beyond a certain gravitational threshold, the degeneracy pressure of neutrons would be overwhelmed, leading to its transformation into a black hole. However, physicists also believe that with a slightly gentler compression, you could create the most exotic type of star in the universe, known as a strange star or quark star, situated between a neutron star and a black hole. It exists in a region where the pressure is high enough to dissolve neutrons and form a strange quark star. However, it is not strong enough for gravity to take full control and collapse all matter into a singular point. The question then arises, what exactly is a strange quark star? It is not something I made up, but rather a concept that physicists believe in. They propose that the pressure at the core of certain neutron stars may be so immense that it surpasses the strong nuclear force holding neutrons together, causing neutron particles to merge and dissolve into quarks. This results in an ultra-dense phase of quark matter existing freely within the strange quark star. The familiar structure of ordinary matter, which includes atomic nuclei and electrons, is completely broken, leaving behind a mass of free quarks swirling in this state. A new equilibrium is established in this state, where a new degeneracy pressure of quarks, as well as electromagnetic repulsive forces, appear to counteract gravitational collapse to some extent. And that, ladies and gentlemen, is a quark star. If the idea presented by Enigma is correct, quark stars could potentially exist and be observed somewhere in the universe. The existence of a quark star is theoretically plausible, but it has not been proven through observations or experiments. The extremely harsh conditions required to stabilize quark matter cannot be reproduced in any laboratory on Earth, and direct observations of quark matter in nature have not yet been made. If quark stars can form, the most likely place to find quark matter would be inside neutron stars, where the necessary pressure for quark deconfinement occurs. They can also form when a massive star collapses towards the end of its life cycle, provided the star is too massive to become a neutron star but not massive enough to form a black hole. This partly explains why quark stars are rare and virtually unobserved. It is possible that someone may have discovered a quark star but mistakenly identified it as a neutron star. Although quark stars, if real, may lack some characteristics of neutron stars, such as the emission of pulsar radiation or typical surface temperatures, as described by theoretical physicists, they are believed to possess distinct properties. Free quarks are considered to have different properties from neutrons. Quark stars may not emit pulsar radiation or exhibit typical surface temperatures like neutron stars. Additionally, quark stars are significantly smaller in size compared to neutron stars, with diameters ranging from 11 to 16 kilometers, as opposed to the 20 to 25 kilometers of neutron stars. However, at distances of trillions of kilometers or greater, this difference is negligible. Both quark stars and neutron stars form at the core of a massive star in a type Roman II supernova explosion. They are both extremely dense and compact, with an incredibly strong gravitational field capable of tearing apart anything at the atomic level. If a quark star is close enough, it is indeed called a strange quark star because it is composed of a specific type of strange matter. If a quark star continues to be supplied with quark matter pressure, it can undergo even stronger transformations and become strange quark matter, distinct from up and down quarks found in protons and neutrons. Strange quarks are significantly heavier, with a mass equivalent to 95 MeV. The issue with such heavy particles is that when they exist in isolation, they tend to decay into lighter particles. In the case of strange quarks, the natural decay products are up and down quarks, with masses of only 2.3 and 4.8 MeV, respectively. However, when a large number of strange quarks gather together, their physical properties can change. Physicists propose that under extremely harsh conditions, even more severe than the core of a neutron star, strange quarks can form bonds with up and down quarks to create more stable triplets, known as strangelets. Strangelets are the smallest fragments of what scientists call strange matter. One peculiar aspect of strange matter, besides its composition of strange quarks, is its highly infectious nature, similar to a highly contagious disease. If strange matter were to be created at the core of a quark star, it would consume the star from the inside out. Below the star's outer shell, it would turn into a mass of strange matter with a diameter of several kilometers, essentially becoming a strange star. Such a strange star would be composed of strange quark matter. I understand that you are envisioning a catastrophic scenario where a sample of strange matter comes into contact with Earth, transforming our planet into a strange planet. The question is whether this scenario is possible or not. The answer is likely to disappoint you. A hypothesis proposed by physicists Arnold Bodmer and Edward Witten suggests that quark matter is the fundamental state of all matter and, therefore, more stable than ordinary matter composed of atomic nuclei and electrons. The nuclei of all atoms, including ours and those of planets, stars, and celestial bodies in the universe, are in a metastable state. After a sufficiently long period or upon receiving appropriate stimulation, they will decay into droplets of more stable strange matter. In other words, the strange matter is so stable that all matter in the universe would desire to become a strange matter for stability. This is where the story becomes interesting or chilling, depending on whether you are a timid person or not. Many people fear that strange matter will transform all life on Earth or, worse, turn all structures, big or small, in the universe into drifting masses of strange matter. However, they overlook the fact that such a transformation would require specific conditions found on Earth to occur. Enigma has spent over half of the video analyzing and emphasizing that strange matter can only be formed and exist within the core of a quark star. One of the most extreme conditions in the universe, the pressure at the core is hundreds of billions of trillions of times greater than the pressure at the surface of the Earth. It is even more staggering when compared to the nearly zero pressure of the vacuum of space. Like an expanding balloon that rapidly inflates until it bursts at higher altitudes where the air is thinner, any patches of strange matter appearing anywhere in the universe, with significantly weaker gravitational pull compared to the core of a quark star, would immediately expand violently, resulting in what I would call a quark detonation. Depending on the location and mass of the strange matter patch, the quark detonation could vaporize an entire city, carve out a crater hundreds of kilometers in diameter, or even obliterate the planet Earth, the third rock from the Sun, along with its over 8 billion human inhabitants. It is undoubtedly an intriguing and visually stunning scenario. However, it is important to remember that there are many ifs between that scenario and reality. Between the hypothetical scenario and reality, there are numerous uncertainties. If strange matter exists, if strange stars exist, and if the strange matter can stably exist under the atmospheric pressure conditions of Earth. What are your thoughts on the possibility of the existence of strange matter and strange stars? Remember to subscribe to the channel and hit the bell to receive updates on Enigma's mind-boggling space content in the future. For now, goodbye and see you again.